The idea is that during this course we'll be replicating another study, and you'll actually be running code from your laptops. For that purpose, we have available a real-life database in the Common Data Model format, the Pharmametrics Plus database made available by the IMS company. So we're very happy with that. I do have some bad news in that the server that it's on, I was just trying it. It's a Amazon Redshift server. It's incredibly slow today, and there's nothing we can do about it. So the code that I sent you is the code that we'll be running, but I simplified it so that it actually will complete.
I don't know if that's just today. Every time I ran an IBID slab against Redshift, it was a painful experience.
So we have one internally in J&J, and I don't know what they did to that, but that's blazingly fast. You can actually scale it up and down as much as you want. So, anyway, but before I do that, I want to just give a general introduction to the package, and then we'll go into actually running some R code. So the Cohort method package is part of what we call the methods library. So what you see here is all the packages that comprise the methods library. Right on top are the packages that are really the specific study designs that we're supporting. So here is the Cohort method package that we'll be talking about today. But we also have a very neat self-controlled case series package, a self-controlled code package, IC temporal pattern discovery package, and a case control package. And so, in theory, we could organize these sessions on all of these. Probably we're not going to do that. Then we have some packages that are basically used by all of these packages. For example, there is a feature extraction package that we already discussed earlier that is used by the Cohort method package to construct the covariates that, for example, go into the propensity model. And here we have the Cyclops package, which is the one packages Mark is leading. That is the regression engine that we're using, the very efficient regression engine that can do the large scale regularized regression that, for example, we're using for propensity models. There's also database connector and SQL render that are specifically for talking to any database in any, a large set of formats and a large set of SQL dialects. So what are some of the technologies that we use inside of this package? So, like I said, we use the database connector and SQL render packages to interact with a common data model that can be on any of these platforms. So SQL Server, Oracle, Postgres, Amazon Redshift, which is what we're currently using for this demo, and Microsoft APS. We use the FF package, which is actually a third-party package, to handle large data objects. So sometimes, for example, when we construct a large set of covariates, that can be more data than would fit into memory, and one of its weaknesses is that it usually doesn't handle that very well. But FF packages, the FF package basically uses your disk as an extension of your memory, and so we don't have any problem running out of memory space. We use Cyclops for large-scale regularized regressions. So before I showed you that in the... Why are you even here?
I never get to hear your tutorial because I always do the other one at the same time.
Oh, okay. Oh, you're welcome. As long as you stay quiet.
It's not going to happen.
That's right. So before the break, I mentioned that in the Cohort method package, basically we broke up the Graham study replications into 5 steps. Getting the necessary data from the database, defining the study population and time at risk, creating a propensity score, doing matching, fitting the outcome model, and throughout generating various diagnostics. That is the general workflow in the Cohort method package, except you may choose to not use a propensity model, which generally is not recommended. And instead of matching, you may choose to do trimming or stratification, or a combination of trimming with matching and or stratification. So this is the general workflow, and in order to demonstrate that, we'll be replicating this other paper that you should have all read, I think, which is by Garbe, which is why the code that I just sent you is called garbe.r. So this study is comparing two NSAIDs, celecoxib versus diclofenac, for the outcome of upper gastrointestinal complications. For this exercise, we've already created, so just sticking to the terminology that we learned before, that means that your T is celecoxib, your C, your comparator, is diclofenac, and your outcome is GI complications. Those three cohorts already exist somewhere on this not-so-fast server that I was just mentioning. So the code will take you from that state, and you will need to move it forward from there. Actually, was ahead of my slide. So we have our TRCRO. The time at risk is simply specified as cohort start to cohort end. And the model specification is that, again, we'll use one-on-one propensity score matching. But instead of using a Cox regression, as was used in the Graham paper, we're using a conditional Poisson regression. And a multivariable one at that. All right, so the way that we've set this up, and we'll see how this goes, is you can simply copy-paste pieces of the code and run it yourself. And probably during that process you will run into questions. But step one is getting the necessary data from the database. And I'll explain what is going on before you actually run the code. Hopefully you're not running the code yet.
Don't listen to that up front.
So we have our target comparator and outcome cohorts that we're going to get from the cohort table, and actually had to modify that in the code that you got because it's called a Garbe cohort in that example. But it's a table that has, back up. There are, in general, when you use the cohort method package, there are several places where we could store these three cohorts. Option one is, in the common data model, there is a table called cohort. That's a general purpose table, and in most situations that's a table that gets populated by Atlas. So if in Atlas you click on generate cohort, it will do so, instantiate your cohort inside this cohort table inside the CDM. It doesn't work like that at all sites because not always people have write privileges on the CDM schema. We also allow you to get this information or store this information in a table that just has the same structure as the cohort table. And so you could have that in a different schema, and you could just point cohort method to that different schema, and you have to specify the table name and get it from there. And that's actually the way that I like to use the cohort method package, because I then just instantiate the cohorts that I need for a specific study. I have my study-specific cohort table, and I know that nobody else is going to mess with that and secretly change it without me knowing, which would be bad. Also, if your cohorts are very simple, your T or your C, your target or comparator, you could actually just use the standard errors that are generated in the drug error table in the common data model. So I hope everybody's familiar enough with the common data model that there is a table called drug error, and there's also a table called condition error, and these contain standard drug errors. So in this case, usually, specifically at the ingredient level, it creates errors of exposure for people. And so you can also use those to define your T, your C, and even your O if you go to the condition error table. And this is supported by the package. One thing that the cohort method can do for you, and that's an option, is it can limit to the first exposure. It can remove subjects in both cohorts, and it can enforce a washout period, so a required amount of continuous observation prior to starting in your cohort. if you may remember before the,
Why would you not do that in the cohort definition?
if you remember,
Good question.
good question.
Been there.
You were going to be quiet. If you had been there, before the break, Patrick showed you that he had actually already done that in Atlas. That is actually the preferred way of working, because then in Atlas already you know how many people end up in this in your cohort, and you can run descriptive analytics on this cohort, and that's just more convenient. However, if you're choosing to use, for example, the drug error table, because you want to run not just on one drug but on 1,000 drugs, you have the option of doing it while loading the data. But like I said, that's usually you do it when you define your cohort in Atlas. All right, so that's our tier CEO, and then we have the covariate. And I already discussed this a little bit before the break. We usually use the automatically constructed default set, that if you just create covariate settings, you basically turn almost everything on true, is what is constructed. You could create custom defined covariates. So if there's a covariate that isn't in there, like a very novel risk score or something that you want to compute yourself, there is an option to do that. There is facilities to do that. You should look at the feature extraction package to see how you do that. But that would require you to write actual SQL code and R code to implement that particular feature. Importantly, if you choose to use, for example, the automatically constructed default set, you need to specify at least the drugs of interest to be excluded from covariate construction, because it actually includes the index date when you construct covariates, and that would mean that you have your own treatment as a predictor of your treatment, and that doesn't work.
And you have to do it by hand if the cohort is done in cohort building.
Yes, that's actually a good thing that you're reminding me. So if you're using drug error, that means that your cohort ID for your T and your C will be concepts. And in that case, there's an option in the package that it will automatically know which things to exclude. But of course, if you're using Atlas, then all bets are off. You're getting a concept or a cohort definition ID that doesn't specify what concepts went into that. And so you have to specify that yourself. All right, so for that we have the getDbCohortMethodData object or function, and I'm just going to walk over go through the arguments that this function has. First argument, connection details, specifies how you connect to the database, and in the code I sent you, it specifies this connection detail object. It just tells you the name of the server, what type of server it is, in this case Redshift, username and password. You now have my username and password. You also need to specify the location of the common data model, data in common data model format. And so we call that the CDM database schema, because what is a database on some platforms is a schema in another platform, so we just contracted the two words to make a generic word. So instead of some people being confused, everybody is confused. We do make heavy use behind the scenes. You normally never see that, of temp tables, and Oracle doesn't support temp tables, or not really. So in order to simulate temp tables, you have to, if you're on Oracle, you need to specify a schema that you have read and write access to that we will use as a pseudo temp table space. But usually, like in this case, we just set it to null because we don't have to. We're not in Oracle. You need to specify the version of the common data model. We're currently supporting version 4 and 5. Unfortunately, Atlas only supports 5, so it's really it's not very useful feature that we found.
In your code, you have a space before CDM5 for a CDM database schema. Is that an error? That's a problem.
I do.
take it down.
Oh, okay, all right. All right, so those are just the arguments for finding the data. Then we have the arguments for finding the exposures. So we have to specify the database schema where these exposure cohorts are, your T and your C cohorts, and that could be the same schema as where your CDM is, or it could be a different one. The exposure table is the name of the table that holds your exposure cohort. So again, so this could be your CDM schema, and the name could be cohort, meaning the cohort table in your CDM schema. In this case, it's not because I created a study-specific cohort table. And your target ID is, of course, the cohort definition ID of the target group, and the comparator ID is your cohort definition ID of your comparator group. And then, as I said, you have the options to remove first or restrict to the first exposure only, remove duplicate people, and specify the washout period. But typically, we do that in the in Atlas. All right. Also, some arguments for specifying study start date and end date that allow you to truncate follow-up time. So next we have arguments for finding the outcome. So we have a database schema for that and a table. And again, this could be your CDM schema, and the name of the table could be the cohort table. And your outcome IDs is one or more, could be many, cohort IDs for your outcome cohorts. And so in this case, we only have one, the GI complications. But if we were to include a set of negative controls, we might have maybe 50 or more. And it will fetch data for all those outcomes at once. Then we need arguments for creating the covariate. So we have our covariate settings object that you create using the create covariate settings function. Like I said, if you're using the drug error table, it can automatically figure out what are the covariates to exclude, to not include drugs. The drugs of interest, in that case, you need to set exclude drugs from covariates to true, and it will use this automatic feature. Otherwise, you will have to specify the covariates to exclude in your create covariate settings function call. The result of this function is an object of type CohortMethodData, and that object uses the FF package to store its data. And that, yep, go ahead.
Sorry, can you go to previous slide?
Yep, sure.
So here you said that automatically exclude drugs of interest only works if the target ID and the comparator ID are concept. So that means that the cohort definition ID has to be the concept ID?
No, that means that if you're not using the drug error table, because in that case your cohort IDs would be concept IDs, but instead you're using, for example, Atlas, then there's no way that your cohort definition ID is going to be a concept ID. You would actually need to specify the concepts to remove elsewhere. So you have the create covariate settings function that has an argument exclude concept IDs, and that's where you would need to specify the things to exclude.
So if you're just writing a manual SQL query using drug error table and calling the cohort definition ID as a drug concept ID, then this would work, like it would automatically.
That's right, because then what the cohort method, what this function would do for you in the background is it would call the vocabulary and tell me, give me this concept ID plus all of its descendants, and then it would say, just remove any concept that is based on these concepts. All right, so I was trying to explain that this object that's generated uses the FF package to store some of its data because it can be really, really large data. That means that you can't use the standard R functions for storing a data object because it would actually lose the link to any data that's written on file. So we have created a function called save cohort method data specifically for saving this type of object. So sometimes these objects can be like many, many gigabytes large. It's not a problem, but just so you know that can happen. Okay, so how can we then produce some diagnostics to make sure that everything went okay when we did the data fetch? So we have the generic R function summary, we can call it on the cohort method data object. And some things that might be of interest as well. Are there at least people in your target comparator and outcome cohort as you extracted it? So here's the number of people in T, the number of people in C, and here are the number of people that have the outcome in the set of people that are either in T or in C.
And if the overlap is 0, is the method going to squeak and say I can't do anything? If the outcome and the population don't have an overlap at all?
No, so but not at this point.
Okay.
At this point, it will just say count is 0, and you can go ahead and you can fit your propensity score and create your study population and whatnot. And then later on, it will say if you want to fit a Cox regression or another model, it will say, but I have no outcomes. So at that point, it will start to complain, and we'll actually give you a warning when you do a call create study population. But that's a different thing.
Just a small question. So now the treatment concept ID is going 1, 2, 3. So if you had generated the cohort writing a manual SQL query instead of Atlas, then what would be the treatment concept ID? There would be like multiple treatment concept IDs?
Well, so when you call getDbCohortMethodData, you can only call it one target comparator combination at a time. So if you have multiple pairs of targets and comparators, you would simply have to call that function multiple times. You can include many outcome cohorts in one call, but just one pair of a T and a C.
Or you combine them yourself beforehand. Well, if you
How would you?
you just merge them.
Well, you can create a very elaborate T and a very elaborate C, but still you can only have one T and one C in one of these getDbCohortMethodData calls at a time. Does that?
Yeah.
Okay. All right, so let's try this. So everybody can start running the code. Oh, don't look at this. This is old. All right, sorry about that. Ignore all that. Blah, blah, blah. Just run the code that I just sent you all the way to where you get the summary on the cohort method data object. All right, so what do we think of these results? Are these okay? Let's do the diagnostic that I just taught
It's
you.
only 17 covariates.
Yeah, so the number of covariates is a little bit on the low side, but that, as I tried to explain, is deliberate because the server is extremely slow.
So you set it to 17?
Yeah.
And when you set it, it just picks the 17? And
No. So I specified it to only create demographic covariates with this
So
17.
it is some useful 17.
Yeah, age and gender and things like that.
I uniform randomly picked 17 out of 10,000, and I hope it helps.
I think you yesterday gave a whole long speech that you shouldn't pick
Yeah.
covariates and it's stupid.
And before lunch as well.
Yes. Go to the principal's office. All right, but we have
You should never.
He did. You said you
Never.
picked
Nice.
covariates.
good. All right, so we do have people in T, we have people in C. Actually, quite that's a respectable size.
Yeah.
And we have people with the outcome. That's actually quite a large number. Okay. A lot of people that have GI complications.
So we've got multiple. I'm probably confused between the last example we used and this example. So we've got 4,000 people who had 6,000 events.
That's right. Yes.
Is that right? So they can. So we haven't specified it has to be first only in this one.
No, so that's something that comes later, if you may remember. So for the outcome.
Oh, so this is just the outcome.
These are just outcome summaries.
Well,
Okay,
so
and not the outcome that we're interested in. Okay, I'm
Well,
getting.
in this,
That's where I'm getting.
they're not combined yet, right? These are separate
Scroll
groups,
back up.
and you could be in
Oh,
one
we are
group more
doing
than
multiple.
once.
Oh,
That's
sorry.
how
Yeah,
it's-
okay.
Yeah, but
That's the outcome.
the point here is that there are more events than people, meaning that
Gotcha. Yeah, no.
people. So there are people that have more than one outcome,
Right.
where the outcome is the GI complication. So there are people that have 2 or more complications at several points in time in their history.
What happens if you duplicate them? Doesn't matter.
That doesn't matter. So, but just to make clear that probably, I don't remember myself, but what Patrick probably did in the Graham replication is already when he was building the outcomes in Atlas, he was saying restrict to the first.
Yes, yeah, I think that's what he did.
And so here we didn't do it, so you could actually have multiple, but then later on if we say remove people with prior outcome,
Uh-huh.
there's actually a reason why we didn't do that here.
Yes, we know.
Oh, you can,
Oh,
Go ahead.
no, why?
because we're doing the puzzle model, and we
That's
can
right.
puzzle women. That, I kind of.
That's
got
right.
At that point. So no, good. Understand.
So I'm very happy we have some multiple events.
Exactly, yeah.
Unfortunately, we only have one subject with 6,530. Oh, 2,000 events and everyone else with one. But
All right, next step, defining the study population. During this step, we select only one of the outcomes of interest. In this case, we only have one, but we can enforce additional filtering criteria, and we can define the risk window, as I also showed before. We use the createStudyPopulation function for this, and that has several arguments. For one, the CohortMethodData object that you've just extracted. The outcome ID, so the ID of the outcome that you're interested in, and in this case you actually can leave this argument out because there is only one. It will automatically pick the one that's in there. You have here again, first exposure only, remove duplicate subject, and washout period. So we now have three locations where we can basically do this filtering. We can do it in Atlas, we can do it while loading the data, and we can do it at this specific location where we're creating the study population. Why this beautiful duplication? It's simply for efficiency reasons. If I were to do a study where I would want to do a sensitivity analysis where I want to change my washout period, I don't want to create two different cohorts in Atlas maybe, and I also don't want to do the data fetch twice, so I can actually specify it over here. And the same goes for the other filtering steps. So that's really why there are three locations.
So sorry, what are you filtering?
So filtering first exposure only means if you didn't filter already on just the first exposure when you were creating your T and your C, you can now say just pick the first error that I have per person. Like if you're using the drug error table, every person can have like hundreds of exposures to the same drug. And here, usually in a new user cohort design, you're just interested in the first one. So here you can say restrict to the first one, if you didn't do that already before. And remove duplicate subjects. Usually you don't want people that are in both cohorts. And washout period is require at least 365 days, for example.
These are
Of,
things you typically do some sensitivity analysis over.
yep. So in that case, you might not want to do them in Atlas, but you want to do them over here. That could be a reason.
This remove duplicate subjects, it's gonna remove the patient from both T and C, or only from T? Or only
From both. So if there, and if any overlap is completely removed from both T and C.
And if you don't like that behavior, then you need to specify more specifically what you want in Atlas, so that those individuals don't show up.
Right, so like I said, there are now three options where you can basically remove duplicate people. And in Atlas, you can actually very clearly say, for the target cohort, you don't throw away people. And for the comparator cohort, you can say, remove people that are in the target cohort. And then you have the behavior that you just
Where do you
did.
do that? In the definition of the cohort?
In the definition of the cohort in Atlas.
Oh, so you just subtract them from another cohort?
No, you can just, you just add an inclusion criteria that says should have 0 occurrences of whatever is the thing that defines the other group.
So, just say not having both drugs at the same time, is this, what's used as the period of time?
So this is more restrictive than that. So basically any person ID that is appearing in both of the cohorts is thrown out.
Like person ID.
Yes. So this is an important one. Remove subject with prior outcomes. But we already discussed it.
Can I just move back one step? So
Sure.
in that example we did this morning, one of the censoring criteria was that they switched medicine. They went from warfarin to dabigatran or the other way around. But if we didn't Patrick exclude them at the start, in which case they wouldn't ever be in.
Patrick excluded them at the start, so they wouldn't be in this situation. But he did.
But that in the actual study, they censored, so they left them in until they switched.
Yeah, until
So
they use that as an exit criteria.
So that's so.
Okay, that could be a difference.
How that would work.
So another argument is prior outcome look back. So if you say remove people that had the outcome before, you can also specify how many days you're going to be looking back. So usually we just have that at 99999, so any time before. But it could be that you just say, okay, just if they had it in the last 30 days, I want to remove them.
Wait until those 40-year studies start happening. So that magic number is going to bite us.
Before you how do you set the number? So it's true, false? And then
No. So this is a true, false, and this is just number of days.
It's not in your code, right?
I don't.
No. This is just what we're running for the example. These are
Right, but
more of the arguments.
Okay.
Yeah, so there are more
So
arguments than might
if
be
you
in
want the
code.
default, you do that. So question mark.
You didn't list all the arguments?
I didn't use all of them in the code. It makes for hard to read code.
Yeah, but on the other hand, people don't know what all the arguments are. That makes it much easier to know what they might be setting, might have to set, because you know it by heart, right?
Oh yeah.
But you just do the ... if you don't want to anymore.
There are those of us that believe in long signatures, and those of us that believe in short signatures.
Yeah. No, but this is if
This
you
needs
want
a
to.
long
The
signature.
problem is if you don't know by heart what all the stuff is in there, then this would help you to say, okay, I have to check it all
Yeah,
off.
all the
Okay.
choices. No, there are advantages of long signatures instead of object classes.
All right, moving ahead because I don't think we're actually don't have that much time.
Set at 15 minutes, and it's 20 minutes until 15 minutes. So we're at like.
All right, okay.
I'm gonna take a long break though.
All right, so we have our arguments for defining the risk window, which basically is the day that it starts, the day that it ends, and then whether or not you want to basically add the whole length of whatever was the length of the cohort to that date. So you can also say, if I say add exposure days to start, I could actually have my risk window start, for example, when people stop taking the drug, which doesn't usually happen, but you could even specify that. Usually this is one is false and this one is true, and the rest are 0.
So the risk window start, the first one is basically the index date. So let's say the patient took a drug today, so that would be.
Risk window start is 0.
It's 0, so that will be like today.
Yes.
And what about add exposures date to start?
Well, so then suppose that my cohort ends, which might be, for example, when I stopped taking the drug, is 30 days from now. That would mean I would add 30 days to my start date, meaning that my risk window wouldn't start until I stopped taking the drug, which maybe doesn't make sense, but in some studies that's what people want to do.
But wait, but it's a fixed 30 days, right? You can't say stop.
No. So depending, if you said add exposure days to start, it basically means that your cohort end date or your exposure end date is what drives when your risk window starts. And so that can be different for everybody.
This could be used as like washout periods.
Yeah, so sometimes people have two studies. One is for what happens when you're on the drug, and one what happens just the period where you stop taking the drug.
So
It's just-
maybe, so in this area, so I've been looking at a problem where I want to look at rehospitalization. So someone's hospitalized, exits, and then I want to start the clock. Would I be using these mechanisms for that?
No, well, I wouldn't. Probably you would just define your index date to be the time when you leave the hospital, the first time, and that's when the clock starts ticking. That's how I would probably do it.
So the discharge date. It's calculated
That's right.
between each
Okay. So just some examples. When you just want the risk window to be the time exposed, you set risk window start to 0, add exposure days to end false, risk window end is 0, and add exposure days to end true. So that's just basically taking the cohort start and end date as defined in wherever you got the cohort from.
Anton, can you just explain to me again, so add exposure days to end means? I don't think I get that.
Yeah, it's a horrible name, I know. Basically, when you set it to false, your reference point is what is the cohort start date. When you set it to true, your reference point is whatever is your cohort end date. That's probably a better way of thinking about it. So
No, when you say reference point, you mean the end of the risk?
well, no.
The index.
So reference point in this case for the start, and in this case, reference point for the end of the risk window.
This maybe dry.
A picture will help
Yeah, I still don't think I get
in
it.
future.
Alright.
For the next tutorial,
Yes.
a picture
No,
will help.
next tutorial, the page stays off. This tutorial is got a picture.
What?
No, next one is a picture. This one we just have to make do with the text.
Yeah, I don't have anything to draw on, I'm afraid, but
So,
Like if you
are
wanted
they
to,
redundant, like is add exposure days to start equal false? Do you always have to change add exposure days to end equal true? Or
No.
can you have both be true and both be false?
yes, you can have that. So let me run through some examples, maybe that helps. So this is just time exposed. This is how you define it. And then some people have an idea of something called intent to treat, which is basically all time following the index date. So in that case, risk window start is 0, add exposure days to start is false. So that means you're starting on the start of the cohort. Risk window end is a really large number, and if we, I don't know how many years, but maybe you want to add a 9 there. And add exposure days to ends really doesn't matter anymore because you're just always going to go on until the end of observation for that person. So that's how you specify an intent to treat that just starts on the index date and just goes on until you have no more observation time for that person. Then we have, for example, time exposed plus 30 days. So you start again on the index date, so risk window start is 0, add exposure days to start is false, and then risk window end is 30. Add exposure days to end is true. So that means you go on to whatever was defined as the end of your cohort, which if you're using the drug error table is the time you stopped taking the drug, and then you add 30 days to that because you may suspect that the effect of the drug will carry on for 30 days after you stopped taking it.
When you put this to true, when does the window start? The risk?
Then it will start at whatever you define as your cohort end. So if you're using the drug error table,
I see.
then it will change your start of your risk window to the end of the exposure, which
So really this should be called set start date to start, set risk date to start, set risk date to end.
well, except that here you also have an offset that you then add to that.
Oh, okay, yeah.
So they're basically offsets.
Yep.
to
Yes.
Yep.
The drug error start date, drug error end date that you pulled from your cohort.
Well, so these are offsets, the start and end,
Dates from the-
and this is relative to what is the offset. So if this one is true, it's relative to the end date, and if it's false, the start will be relative to the cohort start date. But next time I will have a graph which will help. And like you never really use add exposure days to start. I just had one particular example where I needed it, and that's why I added it. But it's seldom happens.
Well, couldn't you for like procedures and you don't want to day of the procedure itself, that kind of thing?
Well, but then you just add one to
Yeah.
start. But
Oh.
you never use add,
yeah.
add exposure
Yep,
days.
yep.
Okay, but moving on. Or you could say, I just want the first 30 days after index, no matter how long somebody is exposed or not. So then you set risk window start to 0, add exposure days to start false. Risk window end is 30, add exposure days to end. So that's just always the 30 days following index, independent of whatever your cohort end date was. And those usually are the options that we use and nothing more. So the result of that function is just a data frame, so you can just use any R function that you like on that object. But there's one function you may find useful. It's called the getAttrition table function, or else the drawAttrition diagram function, and if you call that, it will give you the attrition diagram. This is actually not the one that Mary got, because Mary got a duplicate. Have you already figured out why there's 2 times a filtering of people that are in both cohorts? All right, I'm not going to rack your brain on that one. So, as I was trying to explain, there are multiple places where you can remove people that are in both cohorts, and for some reason in the code, it's set to true in both cases. So it's set to true when loading the data, and it's set to true when creating the study population. So it's trying to do it twice, but the second time it actually no longer has people to kick out because they're in both cohorts. So that's why you see it twice. So it's actually bad of my example code that I had it there. All right. So I think most of you are actually already way ahead, but please go ahead until you get to the attrition diagram. And I will quickly, well, you already have it. All right. Next step, and for most of you already completed step, propensity models. But I'm actually going to explain something here, so you may or may not want to pay attention. So for propensity models, by default, we use a regularized regression. And I have a feeling that most of you are already familiar with this concept, but I will try and explain it anyway. So the propensity model is just a logistic regression model where we're trying to build a model for the probability of the treatment, one treatment or the other, the T or the C, conditional on the covariates that we've constructed. So that usually takes the form of an intercept and then betas for every variable covariate that we created.
All 17.
All 17 in this case.
Wow.
Usually somewhere between 10 and 100,000. In this case, 17. The thing that we do differently in a regularized regression is that we specify a prior distribution on these betas there. So we specify a belief that we have for what the values should be. And we have 2 options that are supported in our package. One is a normal prior, which basically expresses the belief that most of these betas will be small. And we have a Laplace prior that basically expresses the belief that most of them are small, and actually most of them will be exactly equal to 0. So we prefer the Laplace prior because actually what the end result is that most of the betas will be exactly equal to 0. And we can consider them to have fallen out of the model, and we no longer need to consider them. What is the right width of that prior distribution? Well, that's very hard to tell. If we make it too wide, then we'll get convergence problems, because then if we have correlated features, we will have trouble picking one or the other. And we probably end up overfitting our model. If it's too narrow, then we'll get underfitting, meaning that we might miss important predictors in our model. The default setting in the Cohort method package is to select this hyperparameter through tenfold cross-validation and aiming to optimize the out-of-sample likelihood. And that actually, we found out, works pretty well for this problem. So it's now a fully automated fire and forget approach that you just call the createPs function, and it will do all of this for you in the background. So the createPs function has the arguments to create the Cohort method data object, of course, because that holds all the covariates. The population, the study population that you've now created, because it has to restrict to that population. There is an object called prior, an argument called prior, that specifies the prior that you want to use. And so by default it's on Laplace, and actually I forgot to mention that you can also set it to normal. You can also set it to none, meaning that there is no prior is used, and it actually becomes an ordinary logistic regression. And so in this case, because we only have 17 covariates, it will just work fine if you set it to none. If you're feeling clairvoyant, you could specify the variance that you want to use for the for the regression.
In the initial OMOP experiment, we thought we were clairvoyant. Turned out we were off by over an order of magnitude.
Too big of this one.
Yes.
Or if not, you can specify to use cross-validation, yes or no. And you can specify covariates to exclude from regularization. By default, the one that is excluded is the intercept, for hopefully obvious reasons. Next to that is a control object that basically controls mostly controls a lot of things, but basically controls the regularization, or at least the cross-validation. You can specify things like the tolerance, so the precision that you want when you're optimizing the likelihood function, the number of folds in the cross-validation. CV repetitions is there is a sampling going on when you create the folds, and you may end up with a very unlucky sampling. And so if you want to be absolutely sure that you're really estimating the performance of a particular hyperparameter value, you want to have multiple repetitions of your cross-validation. So you can actually say, I want 10 cross-validation, and I want to do that 10 times, for example. That's something we sometimes do when we really want to be sure that we're fitting a good model. And, not unimportantly, you can specify the number of threads used during the cross-validation. You can imagine if you're doing 10-fold cross-validation with 10 repetitions, and you're doing that on a very large data set, then this can become a very computationally heavy exercise. You can spread it out over cores, but it only works on the cross-validation. So if you have 10 folds, then basically the maximum number that makes sense for threads is 10, because it's not going to use any more than that.
No, it works over the replications too.
Oh, it works also over the replication. Okay,
But any computer hardware, the bandwidth isn't going to give you speed up.
Yeah, so we've actually been playing around with that, and at a certain point, of course, the more cores you use, it doesn't mean that you're actually becoming faster, because you're starting to hit other bottlenecks, such as memory access and stuff like that. So I usually keep it somewhere between 20 and 30.
So if we don't put it, just what does it do then?
So if you don't specify, it uses 1.
Oh, wow.
Yeah, so that's not usually what you want. So do keep in mind, if you start working with larger data sets, this becomes your friend, because it means it's...
And why would you not give it some heuristic between folds and repetitions?
Well,
so
we...
like number of folds times number of repetitions kind of thing?
Oh, the real reason, because we're lazy.
Okay.
Arguments against, you don't want to assume that this is going to be the only task running on the system. And so the user has that knowledge, and so the user should provide that.
But the user doesn't have the knowledge what actually happens under the hood, and so
No.
therefore they have no idea what.
Yeah.
Is it in the function?
Yeah.
Yeah, it's all there.
It is in the help. So, but like...
I mean, you don't want to set it to like 10, because then if they're running something.
If you.
I mean, there are certain...
This is your machine. You should do whatever you want.
Yeah.
Okay, good.
Good. All right, so this function returns, again, a data frame. It's actually the same data frame as that went into it, but it will have an extra column that contains the propensity score.
10 hours later, one extra column.
Exactly.
How many covariates? 10
Oh, it's not. It's more a function of the height of the data set than the width. And the number of cross-validation and the hardware that you're on.
Can you go one back?
Okay.
Seconds.
Population. Okay,
Yeah.
that's why you have one column for propensity score for each one.
Exactly. Yeah, so the result is basically this object that went in, but just adding a column.
Yeah, so not many people.
Is it Cyclops running under code that's doing?
Exactly.
this? Okay.
All right, so diagnostics for this step. Well, so first step is we've actually built in a feature that is an extremely useful feature. That is, this function will stop very soon, very quickly, if it finds that one of the covariates is almost perfectly predictive of treatment, because that usually, well, almost always is an indication that you misspecified your model. So you probably forgot to exclude the drugs from your covariate set. So the first diagnostic is that you actually were able to complete the function without hitting this error. The next step is you compute the AUC of this model, but there is a bit of a problem there in that we don't really have a recommendation of what you should see. Because if the AUC is 0.5, that could be for two reasons. One is we have a really bad model and we're just not able to predict, or you have a really good model, but the populations are completely comparable. So one is really bad, one is really good, and then we have no recommendation. We do know that if the AUC is 1, well, again, that could have two reasons. One is maybe you still had some very predictive things that that first check didn't find, or your populations are really completely different. So it's, people always talk about the AUC of a propensity score, but I'm not really sure how to what to do with it. All right, so one that is very useful is the function getPs model. What that will do is it will give you back the model that was actually fitted. And as I just explained, when you use the Laplace prior, or in the case when you only have 17 covariates to begin with, that model should be something you can inspect. So at most a few hundred covariates. And it will rank order it by the magnitude of the beta. And so you can see which are the variables that are most predictive of treatment. And there you might find some things that are not the things that you want.
So if you have 100,000, then what you're saying is all of them are going to be just have a small effect. The ones, even the biggest ones, are going to be all small fry.
Well, so if you start with 100,000 covariates and you use your regularized regression, then maybe 200 will have a non-zero coefficient, and you only have to look at those 200, and you rank order them by betas anyway, and so probably the first 10 are the ones that are most informative.
So how do we do that on what we've just done? So you say getPs model.
I think that's actually, that should be in the code. Yes.
The as propensity model was the top one. Are the variables normalized so that the magnitude of the coefficient is a true representation of its importance?
That is a very insightful question. Yes, the variables are normalized before fitting the model. That means that
They're comparable.
that means that they're actually comparable, and so the beta is more or less the importance of each variable. All right, and the one that I personally like most is run plot PS to generate the actual distributions.
And so the previous ones.
This is what most studies look like, but nobody reports it.
Yes. So this is good. You have large overlap. They're comparable. This is bad because they're really different, the two populations.
Graham just got really lucky.
Yes.
So this one here, the previous one. So if there's one where you're saying, what the hell, or what are you doing there? So something where you're saying, I would have never expected that, so...
Well, so sometimes there are things there that you wouldn't want. So what if the prescribing of a drug is dependent on the physician doing a particular test, a procedure, and the procedure ends up in the model? Then you can argue that that particular covariate just should not be in your model fitting.
Because it's a de facto substitute for the...
It's actually part of, you could say it's part of the exposure itself.
Basically, all you're doing is the density.
Yeah, okay. Which is why you can't automate that step at all.
Yep.
We should figure out how we automate that.
So we're at 217.
Yep, I know. Let's go. All right. You need to try it yourself. The reason why this plot looks really crappy is because it's 17 covariates. I'm sorry about that. I really wish we had a more powerful server, because all the code that you're now using would also run with 100,000 covariates, but not fast enough.
If we wanted to run it on all covariates, is there like a parameter we can set to run on all? Or do you always just set the number?
No. So the create covariate settings function is the thing that specifies which covariate gets constructed. And so currently, if you look in your example code, the create covariate settings function only has create demographics covariates to true, and then age.
So is the commented out version of that, is that what we should run in order to?
No, so that one, what that will get you is the covariates used in the Garbe paper. If you want to run everything, or you can call up the help function of the create covariate settings function, and that will give you everything that you can turn to true. What I would recommend is there are two switches that are called create interaction with year and create interaction with month. I would recommend you don't turn those to true because those are more experimental features. They should work, but
Also, it's like when it was done. When it was done.
interactions between everything.
Is that when we are in overtime with the index date
So
as a covariate?
no, so
Just if you cross out.
it will create all interactions between every variable, the interaction term with the calendar year
Oh.
and with the calendar month.
There are a lot of those months.
So
There are like 12 of them.
And Garbe, how many did he put in?
not that many. Those are the habit bunch.
And we don't consider it, or nominal.
Also, if probably a very good resource to mention is if you go to GitHub and you go to the Cohort method package repository and you scroll down a little bit, there is something called a vignette. There actually are two of them, and a vignette. The vignette also takes you through. So it's a vignette is basically an R document that describes step by step how you use a package, and in this case, it will also show you exactly how to run a study. In this case, actually very similar to this study, but there it is the code for generating all covariates. So
I have a question, so demographics month, that's the observation month,
that's right.
and demographics year is the observation. So that's for the condition to break, or this draw.
That's on index date. So that's the index date of your T or your C.
So T or C, or
Well, so if you're in T, then it's the index date in T, and if you're in C, it's the index date in C. And all right, moving on. Well, I'm just going to assume you'll be running this code anyway. I'm going to plow ahead. Blah blah blah. All right, matching, stratification, trimming. So once we have our propensity score, we can match, stratify, or trim. And we have functions for each of that. So what matching does is for every person in the target group, you pick one or more people in the comparator group. Stratification means you simply stratify based on the propensity score, and it will automatically create strata that are equally sized, the number of people.
How many?
You can set the number of strata. It's an argument. And trimming is you can choose to actually eliminate people on each side of the extremes.
If you don't do comparator, but you're saying give me matched from anybody or from non-treated, so it's a whole lot. Is it the same? You just make the cohorts that way?
Yeah.
Okay. So the comparator then is everybody?
Yeah.
A gigantic thing?
Yeah, but it's not recommended
Because?
because that's not really a comparable group. You're usually comparing
Compared to
people.
the guys who didn't get treated, but they're exactly the same because you matched them perfectly well in the...
No, it doesn't work like that.
matching.
We've actually,
You tried that?
well, we've replicated somebody else's study where they did that, and that just ends really badly.
So you get bad blue and red mountains?
Yep. And even if you then afterwards match and manage to get your covariate balance in order, when using the negative controls, you see that you're still extremely biased. You should never compare to a non-user population, is my general recommendation.
That's what Schneeweiss used to say.
Did he also say that?
Oh yeah, he's
Yeah,
like
oh, well-
furious.
Well, no,
That
he's
compared
right.
to
He's
nothing.
a clever guy, you know. So.
but did you say never compare to a non-user?
That's right. So there are
What
people.
if you match using propensity score matching to a non-user?
You just said that.
It still doesn't work?
Well, so we've replicated somebody else's study at one point where they had actually done that. And so first of all, you see that the propensity score distributions are really far apart. then even if you do matching and you see that your covariate balance tells you that you're getting balanced, we then used negative controls and saw that even after matching, you still have an incredible amount of bias. So it's just not something you generally should do. Because there are differences that you can just not adjust yourself out of anymore using propensity score matching. I think the primary reason has to do that it's not so much that it's different people, because that's the thing that you can correct for with a propensity score. It's also the time in their lives. Because the day when you start taking a drug for you is a very special day. And the time following that is also special in that you're in the system and you're seeing your doctor and whatnot. Whereas if you just pick a non-user population, then what is your index date? Do you just pick a random day out of their calendar? Well, then usually on that date nothing is happening, and the weeks after that also nothing. So if you can pick a...
But if you compare to like a
random drug.
some random drug, there's
Oh,
not those.
So then you have a comparator.
So,
Much better than.
so in this replication study that we did, what we did to fix it was exactly that. So we said, okay, you have to at least start on a drug. And we also made some other additional inclusion criteria to make them already more comparable. And then actually you saw that the bias went away. Yeah. So
Interpretation of that though is a bit off, though, because the whole idea of the propensity score is to say, okay, these two people as similar as possible. This person got that drug, this person got that drug. They could have had either, realistically, but they just happened to get this from that one. But if you've got one drug versus some random drug, it doesn't really work. Just like I don't think it works if you've got something like Panadol compared to an opioid. In a doctor's mind, there's never going to be a situation where you've got the same person. Oh, maybe I'll give him Panadol, maybe I'll give him an opioid.
yeah, so I definitely agree. You're on very thin ice when you start making comparisons like that, and so the negative controls can give you some assurance on that it's still a right comparison. But even in that case, yeah, you're right.
So you've got to, you can get comparisons, but is it really what you want?
Yeah.
Is it really the question you're trying to answer? I think you can do it, and they look the same, but yeah.
Oh, and also
generalizability.
Exactly. Yep. Yep.
We should just demand that every doctor prescribes a whole ton of random placebos so that our databases contain those for comparison.
All right, I'm going to go very quickly through these functions. So we have functions for matching, and so things like caliper and the caliper scale and the max ratio. We also have a function that allows you to match on the propensity score and something else. So some people, for some reason, do this. They say, I want to first match on age, and then within every age category, then I want to match on a propensity score. The functions actually allow for that, but I don't.
So some of the covariates are more equal than others.
Exactly. Yes. Stratify. Well, not surprising. It has an argument for number of strata. Sorry, going very quickly here. There are two types of trimming: trimming by propensity score, that you just trim a certain percentage, and trim to equipoise. That's something that Alec Walker proposed, that you first transform your propensity score to a preference score, and then you say everything that has a preference score lower than 0.3 or greater than 0.7, I will throw away. And that's extremely restrictive, but you are making your populations very comparable.
What's the preference score? Or is it not obvious?
It's a transformation of your propensity score to account for the ratio in size between the two cohorts. All right, but anyway. So diagnostics for this particular step, for the matching, the trimming, and the stratification. So again, so you can use the attrition table and draw attrition diagram functions to see whether you still have any people left. Because if, of course, the two groups are very, very different, and you say, I want to do trimming, then, well, if you trim to equipoise, you just lost everybody. More importantly, probably, is you can use the compute covariate balance to compute the covariate balance before and after matching or trimming or stratification. And that usually should look something like this, but I think you already explained that before the break.
It's much better. Look at that.
Yeah.
Perfect.
So all 17 covariates
Oh, squished down.
are
Oh, got whacked.
perfectly imbalanced after matching. So that's proof that our method works. Sorry. I'm going to actually skip ahead even more because we have 3 minutes left. Last step is fitting the outcome model, where we have a couple of options here that Patrick already explained the different models like, so you can choose between logistic, Poisson, or a Cox model. Important feature is you can choose whether or not you want to condition on the strata. So a condition analysis basically performs the analysis within each strata and then accumulates the result across the strata. That's one way of thinking about it. If you're doing stratification, then you have to do conditioning on the strata, or else your stratification has no effect. There are people that perform matching and then don't condition on the match sets, and there are people that do, and that's like a religious debate that I'm not going to take a side in. You can also choose whether or not you want to include covariates in the outcome model. So you may or may not already have adjusted using a propensity score, but you can also then include even more covariates into your outcome model. And so one option is to just use all the covariates that you used in your propensity model and also include them in your outcome model if you so wish. If you do that, what will happen by default is that there will be regularization on all of these other covariates, but not on the treatment variable. Because the treatment variable is the one that you want an unbiased estimate of, and you want to compute confidence intervals, and that's not something that you can easily do when you use regularization on that variable. So all of these are not very surprising. So again, we see our prior object and our control object because there is an option to do regularization here. So I've explained these arguments already before. So diagnostic, well, you could run the plot Kaplan-Meier function. One thing to keep in mind there, and actually the Cohort method package will throw you a warning. If you have strata in your data, a Kaplan-Meier plot has no way of dealing with strata. So it will show you the Kaplan-Meier plot without any consideration of the strata. It means that if your strata is somehow removing bias, that stratification, that adjustment is not visible in the Kaplan-Meier plot. So that's something to definitely keep in the back of your mind. That's something I still need to think about because I think that's a solvable problem, but we currently haven't solved that.
I mean, if the number of strata are small, then you have separate Kaplan-Meier curves.
You could have, small number of strata, you could have Kaplan-Meier plot per strata.
But if it's a matched set, maybe not.
Yeah. Well,
Yeah, I would start to look at the residuals for the matched set. Sure.
Anyway, this is the current state. All right, I think people already did that, and actually this is no longer what you should get because we switched to something else. All right, so just wrapping up. In general, the study steps are getting all the data from the database, defining the study population, may or may not want to choose a fitted propensity model, you may or may not want to trim, match, or stratify, and the last step is fitting the outcome model and throughout your generating diagnostics. There is a part of the Cohort method package that we use a lot, but I haven't touched on at all during this tutorial because that's the advanced tutorial. There is something that we call the all-by-all support that basically allows you to specify a large set of drug or target comparator outcome triplets, a large set of analysis setting, where an analysis setting is something like the choice of whether you want to do matching or stratification, your risk window definition, etc. So these are all considered analysis setting. And you can throw these two buckets of choices into the package, and it will find the most efficient way to compute its way through all possible combinations of target comparator outcome triplets and analysis settings. And it will use like multi-threading and whatnot to get as fast as possible to a large set of estimates and diagnostics for all of the questions that you threw at it. And one reason why you might want such functionality is, well, sensitivity analysis, so you can specify a large set of analysis to run through. Maybe you want to include negative controls, so you can have multiple drug comparator outcomes, or multiple outcomes in this case. I use it for methods research if you want to try a whole bunch of different scenarios. Or you might even want to consider something like safety surveillance, where you're just running through a large set of questions and want to see, or even comparisons. Like results that I presented yesterday are run through this approach.
And then you create this 30,000 plots and you go through them one by one.
Exactly, yeah. Of course, something I also didn't, well, I mentioned it already several times, we do very strongly recommend negative controls as a study diagnostic. So we add diagnostics throughout the process, but we consider the final diagnostic to be at least including negative controls. And, well, negative controls are outcomes not believed to be caused by either exposure. And so we want to observe the distribution of estimates when we run our entire analysis on a set of negative controls. And so usually you get something like a plot like this, where every blue dot represents the relative risk and standard error for one of these negative controls. And you would like it to look like this, that only 5% of your negative controls are below the dashed line, meaning statistically significant.
But the method, the package doesn't build this. This is something you have to do by hand afterwards, right?
Yeah, so that's not inside of the Cohort method package, although things like building these neat plots is in another package called empirical calibration, which is also part of the methods library.
But running the negative controls isn't Cohort.
Well, so
you would run all 50 plus your own analysis within Cohort method.
Yeah, but then you have to plot this, and then you have to scratch your head. So there's nothing which takes the pay, which are in code. Okay.
Yeah, it's just another load library, scratch head.
Yeah, no, I'm
yeah.
It's there.
All right.
You guys do all these automations, you never know.
So just very, very quickly, because we're actually out of time. What did the folks in the other track learn? Well, they learned how to use Atlas to create cohorts. So I guess you're all now feeling sorry that you didn't go there.
Or vice versa.
So they'll now be able to do that, hopefully. They also learned to think a little bit more about study design, and so whether or not you want to use matching or stratification. And they learned how to use Atlas to generate starting R code. So I think Patrick already showed this feature where you can click through Atlas and it will generate a set of R code that basically already performs a study using the Cohort method package. Although usually you'll find that needs just your starting point.
It's the page where it asks for all the parameters and then call it.
It still needs some love. You can't just assume
blindly let it run. What was it?
You can't just assume copy paste. Oh, it still needs some love.
Yeah,
some attention, some finessing.
No, that's not. What?
What does love mean to you?
I don't know. This is a foreign concept to me. What is the R code?
All right. Thanks, everyone.
What does the code mean?